We are Team Air from Chicago EDT at University of Illinois Chicago. We build drones, fly drones, and participate in robotics events and competitions. We have competed in MRDC competition at University of Illinois at Champaign, and we also participated in STEM Fest at Northern Illinois University. This year, our main focus is SUAS 2024 competition. As we in the process of developing our drone, many challenges and mishaps occur, but there are also joys, excitement, and happiness. Introducing our team: Captains, Manfarm, CS Leader, Aviasic Leader, Mechanical and Electrical Leader. Members: Devin Duan, Sean Mehta, GCS Operator, Adrian Say, Safety Pilot, Ethan Key, Tyler Pham, Noreen Vasquez, and Samuel Figueroa. Officers of EDT: Treasurer Adrian Velasquez, President Carl-Jan Stalev, and Vice President Frank Tashes. We want to thank our alumni for supporting our team, Christian Sanchez and Adam Eigel.
Alright, let's start off with some technical design. So, for our drone, we had some requirements. This included that the drone should be able to fly a mission for 20 to 30 minutes, should be able to fly for 5 miles, and if there are any errors on the drone itself, it should be able to safely land and return back to where it started. For the payload, we decided to only try for a single water bottle for simplicity's sake. And for imaging, we wanted our targets to be a 40 by 40 square. And we found that the IMX 477 with a 60mm telephoto lens would give us that from 75 feet in the air. Now these images are fed through a YOLO V5 model running on our Jetson Nano to get us coordinates and direct the drone. Next, we have our drone itself. It is a hexacopter running off of a Pixhawk 6C. It is 3 feet wide and can fly for approximately 20 minutes at a time off of a 6S 25 amp hour battery. We have Lumineer motors and Hobbywing ESCs powering those motors. And for our ground control station, we have one of our laptops running Q ground control. Attached is a RFD 900X radio module, one on the drone itself, and on the drone attached to the Pixhawk, and one attached to our laptops. And with the Jetson, we have a Wi-Fi antenna attached to the Jetson itself on the drone, and we are using a TP-Link router to connect to said antenna. And finally, for manual flight, we're using a TX16S controller.
Okay, so now let's get into the imaging and object detection, design, and testing. So basically, we wrote a simulate images script to create images with a target on a specific background. Some of those backgrounds include the green miller, which is the green grass, the yellow miller, which is the yellow grass, and the airport field. Now we did this because we only had access to local parks and not an airport field, which is where the competition takes place at. We also added a setting to the script which allows us to change the drone height. As you can see for the images on the right, the drone height for the top image is 75 feet, and the drone height for the bottom image is 20 feet, and the target size in the bottom image is larger than the one in the top image. We use the YOLO V5 model because it takes less space compared to the YOLO V8, and it is more supportive with the Jetson Nano. Anyway, we fed a bunch of these images into the YOLO model to train it and detect these images and specify the shape of the targets. We also wrote some code that allows us to detect the coordinates of a target within an image. For example, we have 3 targets here. Each one has their local coordinates, and then with those local coordinates, we convert it into global coordinates or latitude and longitude coordinates. And then with those coordinates, we also calculate the distance between all the targets and the center point right here, with 14.75 feet, 8.92 feet, and 10.9 feet. And we use Google Maps to debug the image because Google Maps seemed the most accurate when it came to distance. Now as you can see, for the red target, the distance is off by 1 foot, which is okay. And the same thing goes for the black star, and for the white circle, which is off by 0.01 feet. To put it simply, the program is 96% accurate when it comes to calculating the distance. We also installed a camera onto the drone and took pictures of targets with it, and one of the pictures looks something like this. Now there is a lot of static, but you can clearly see the target here. Also, the drone was 40 feet above the ground when this picture was taken.
Onto our airdrop design and performance. Here is our winch design. Our current mechanism is a DC brush geared motor with a 60mm spool press-fitted into the motor. We use an Arduino system which consists of an Arduino box with the LM298 motor module to control the speed and direction of the payload drop, utilizing a 60mm diameter spool with a fishing line attached to a C-clip to hold the payload in place. This is a video of our current winch design in action. The 20 fluid ounce bottle descends from the top of the railing to the floor in just 4 seconds. The minimum altitude for the airdrop is 75 feet, which is 6.25 times the measured height in the video. Extrapolating to a height of 75 feet, we estimate a total drop time to be less than 30 seconds. To determine the optimal drop time for the payload to land safely, the team tested several different radius sizes for our spool. Increasing the diameter of the spool allowed us to unwind more wire with each rotation. However, larger spools occupy more space and add more weight. After careful consideration, we settled on a 60mm diameter spool, as this reduced our drop time to under 4 seconds from 12 feet. From the video, we saw the motor spun steadily at this size, confirming its suitability for our winch. Here are some of the alternatives considered. We also considered a brake design as an alternative airdrop method, similar to what's seen in cars and bikes. This brake slows the water bottle's descent time by clamping a disc tied to the spool, which we use a rotary encoder to measure the beam brakes for position, velocity, and acceleration calculations. We used a larger contact area and applied a rubber sealant to boost the friction. The bottle speed is adjusted by pulsing the brakes, which is similar to ABS, while the C-clamps brake upon rapid acceleration. This design was abandoned due to the high power consumption from holding the water bottle during flight, which is why we decided to stick to a traditional rotary winch design.
Our communications and electrical design. This is a broad view of our electrical diagram. This is our illustration of all communication systems used in our setup. Our Pixhawk communicates with the Jetson by a serial connection with Mavlink protocol. The Jetson can be controlled by the ground control station using SSH through wireless LAN using a router. To monitor real-time flight data, the Pixhawk communicates with the ground control station with RFD 900 wireless modules. This can be the same computer. To control the drone manually and switch flight modes, we're using a transmitter with Express LRS telemetry. To visually monitor the drone and easily fly it manually, we're using an analog FPV video system. Lastly, the remote ID transmitter, which is an independent module, broadcasts the presence of the drone to comply with FAA law. With long flight distance requirements, telemetry range is important. Therefore, we did testing and this is our results on maximum range.
Shown below is our hexacopter design rather than SolidWorks. The drone was designed based on the following 4 key pillars: ease of manufacturing, modularity, cost effectiveness, and iterative refinement. Additionally, aerodynamic performance is prioritized, leading to a narrow, streamlined shape that minimizes drag. We also considered weight reduction in our design process, and the propulsion system is powered by 6 motors symmetrically positioned around the drone's body. To enhance modularity, our team devised a unique approach to design the body frames and landing legs. We strategically integrated multiple holes across the frame to facilitate easier reassembly of drone components, ensure organized electrical wiring, and minimize the overall weight on the drone. Additionally, by incorporating holes along the landing legs, we explored alternative battery placement options, testing the drone's performance with batteries positioned on the sides rather than on top of the frame. This adaptability underscores the versatility of our design. 4 distinct materials were employed in constructing the drone. For the frame, we chose acrylic due to its durability and ease of laser cutting. PLA material was chosen for landing legs for its strength, affordability, and ease of replacement. For the motor clamps, we used PETG material since it offers a decent impact resistance and effective vibration dampening. Lastly, carbon fiber was employed for the arms, linking the drone body to its propellers, since it provides a lightweight yet robust solution to ensure balanced flight performance.
For the flight performance requirements, we highlighted requirements in blue that are specific to our drone. We're able to achieve all the requirements except the first one, where drone has to fly for 5 miles in a single flight, as our drone can fly maximally 3.3 miles. We report statistics of our drone flight performance, and some of the required statistics are number of autonomous flights, 15, average amount of time spent in manual mode per flight is less than 1 minute, number of waypoints hit is maximally 33 waypoints, average waypoint miss error is 0. We also do some more statistics to measure the maximum capability of our drone. So the longest distance is 3.2 miles, longest flight time is 22 minutes, longest manual control distance is 320 meters, average speed is 10 kilometers per hour, and maximum altitude difference is 43 meters. Moving on to safety risk and mitigations. Our main concern with safety was avoiding any possible collisions with the drone. We tested autonomous flights in a clear area at low elevations, monitoring from safe distance. To reduce the effect of components failing, we use nylon lug nuts and Loctite to secure hardware. As we talked about before, we chose the hexacopter design, so we have some redundancy in case a motor or propeller fails. We had several of our members take the recreational UAS safety test and also register our drone with the FAA. This is to ensure that our safety pilots and our drone follow the safety rule. This year, we achieved great autonomy, and we are able to command failsafe for the drone. In the case where safety pilot could not control manually, or drone lose connection to ground control station or radio remote control, we always have option to switch to hold or return to launch or land mode. Some areas that we fly are very restricted, and we have option to set up geofence so the drone can stay within the boundary. For the full mission testing, since this year our main focus is the autopilot, we do not focus much on other area to conduct an integrated mission test. Everything is separate to test right now, but when it comes together, we haven't produced good result. The only integrated test that we have conducted so far is drone with attached camera and taking photos in search of target. The resolution of the image is expected, and the ODLC algorithm correctly detects targets. The critical section for this video is proof of life, which dedicates to the safety and the robust autopilot requirements.
We did a majority of test flying at an RC aircraft flying field. Our first test flight was flying manually at line of sight. To make sure we have adequate telemetry range, we decide to fly manually again, but this time to a distance of 1,000 feet away.
Oh, alright. Alright, nice. Let's go. Finally. Alright. Alright, bring it right back. Oh yeah, the range, that is perfect. 1,000 feet, that is good. Alright, gentle landing, please. Okay.
We also tried testing automatic landing.
Mission accomplished.
Now we test our autopilot by setting some waypoints. Despite the wind, the flight is quite smooth. Near the end of that test flight, we also decide to try testing automatic return to home. For what we called a cardio test flight, we set many waypoints for a total of 2.2 miles of flight.
Oh, it's flying up. 2 mile. Wow, okay.
This flight was about 13 minutes long, however at the end we had considerable battery life left, so we could have flown even longer.
In summary, this year we achieved the safety and the autopilot requirements. One requirement that we did not pass is the 5 miles, as our drone achieved 3.3 miles. However, we believe that our drone can still compete given that our drone is capable of taking photos and airdropping. Although we encountered a few mishaps during testing, we continue to learn from them and safety is a major consideration. We are very optimistic that with successful autonomy, we'll be able to conduct integrated mission flights in the summer before competition date. Ultimately, we dream to enter the competition not just to compete, but to learn about drones from talented universities so we could improve our drone. Thank you for watching this video.